I'm Yohei Onuki at the Kyushu University in Japan. Today I talk about the breaking of internal waves simulated in a distorted domain model. The collaborators are Sylvain Jobod and Thierry Doxor, both are at ENS Lyon. And also we are now collaborating with Manita and Matura and Abiran DS at IIT Madras. In today's talk, I will show a summary of two papers published in JEF-CAM and JPO in the last 3 years. I will also mention latest topic collaborated with Mani, because I do not have enough time to explain the details of these two papers. If you are interested in them, please check these articles. The basic motivation of this study is to fill in the scale gap of the ocean's energy cascade. As Carlsen explained in the lecture today, the ocean's internal waves are originally forced by winds and tides at large scales, typically hundreds of meter wavelengths in the vertical direction. This wave energy is transferred towards smaller scales via nonlinear wave interaction. The internal waves break to produce turbulent motions. Small-scale turbulence dissipates kinetic energy and mix the stratified seawater against the gravity. The quantification of this turbulent mixing is one of the major challenges of physical oceanography. And most of numerical ocean models can resolve the generation and propagation of internal waves, but they do not resolve the wave-breaking processes. There remains uncertainty as to what kind of instability is responsible for the wave breaking. Also, the ratio of the viscous energy dissipation and also the mixing against gravity, which is often referred to as mixing coefficient gamma. The actual value of this mixing coefficient are still under the debate. So typically, the mixing coefficient gamma is assumed to be 0.2, but the ocean observation research reports that significant variations exist in the deep ocean. And it is assumed that this gamma may be dependent on the wave breaking processes. Therefore, the understanding of the internal wave breaking in the ocean is very important for us. To tackle this problem, we have been developing a new numerical simulation technique. Now I am showing the basic concept of a numerical model. We consider large-scale fluid motion in stratified fluid. Then we cut out a small domain that is temporarily distorted by a large-scale flow field. In this time-dependent frame, we simulate the fluid motion and resolve the internal wave breaking and the resulting turbulent dissipation. In this model, the large-scale flow field is parameterized by an exact solution of the original governing equation. Therefore, we do not need to resolve this large-scale fluid motion. This is a great advantage of this numerical technique. There is a fundamental theory underlying the idea of a numerical model. This framework is sometimes called the local stability analysis, as Mani explained in his lecture today. In this theory, we consider a solution of fluid equations as a superposition of the large-scale flow field and the small-scale disturbance, which is a WKB ansatz. Inserting this ansatz into the original equations, we derive a set of ordinary differential equations that govern the wave numbers and wave amplitude of the disturbances. The stability of the disturbances is analyzed by numerically solving this set of equations. The Mani shows the application of this method to plane internal and inertial gravity waves in his talk. Now we extend this model to a free nonlinear system. In the same way as the linear case, we consider a superposition of a base flow component and disturbance waves. The basic step of our model is to approximate the base flow components as a linear functions with respect to the spatial coordinates. the coefficients of these functions can be either constant or functions of time. We then apply a time-dependent Fourier transform to the disturbance component. Different from the usual Fourier transform, the wave numbers k are now functions of time. Conceptually, this transform is equivalent to the usual Fourier transform with respect to time-dependent coordinates. I am illustrating the situation in this right panel. The original spatial coordinates are now x1, x3. Now we transform these coordinates following the shared base flow. Okay. The new coordinates, time-dependent coordinates, are GUZ1, GUZ2, GUZ3. Okay. So if we consider the Fourier transform with respect to these time-dependent coordinates, GUZ and write it as k tilde, this k tilde is fixed in time, then transformed back to the original coordinates. Now the transformed wave number k varies with time. And we write the Fourier coefficients for the velocity u prime and b prime and u as u hat and b hat. And these disturbance coefficients obey this set of equations. Now, this equation system includes nonlinear terms and viscosity and diffusivity. If we neglect these nonlinear terms, the set of equations are equivalent to the case of the previous WKB methods. That is why we can call this model as a natural extension from the classical local stability analysis theory. There are several advantages of a model. First, in a model, we do not resolve the large-scale flow field. Therefore, we can concentrate our computer resources on resolving the small-scale turbulence. Second, because we are using a Fourier spectral method, the precision is much better than the usual finite difference method. Third, in our model, the wave energy, that is the kinetic energy and available potential energy, are supplied from the base wave through these terms. And these terms involve the spatial gradients of the base wave velocity and base flow buoyancy. Okay. In many direct numerical simulations of homogeneous isotropic turbulence, people include artificial external forcing term. In our model, we do not need such a term, and the energy supply to the disturbance is specified by a small set of parameters. The parameters are the spatial gradients of the base flow components. Now, we first show a basic example of this situation. We consider an elliptic-shaped vortex. This is a typical situation at the submesoscale ocean. When Rossby number is close to 1, in this situation, the so-called agisotrophic anticyclonic instability occurs. This instability is similar to the symmetric or inertial instabilities, but because we do not require the sign reversal of the potential vorticity, the condition of this agisotrophic anticyclonic instability may be satisfied more ubiquitously in the broad area of the real ocean. The basic mechanism of this instability is explained in terms of the parametric resonance between the vortex and the inertial gravity waves. I don't explain in detail this mechanism. I will just show you some movie later. And this is the detailed calculation conditions, and I skip the explaining detail of them. In our study, we carried out 58 runs changing the parameters. Today, I demonstrate the basic result of one case. So this is here. I am showing the density on the surface of the calculation domain. Here, the black curve represents the streamline of the background vortex. Following this curve, the calculation domain rotates while being distorted. So with time, we can see a periodic undulation isopycnal surfaces associated with the excitation of internal gravity waves. When the wave amplitude becomes sufficiently large, density of water occurs, and the wave suddenly breaks to produce small-scale turbulent fluctuations. So in the parametrizations experiments, we identified two different scenarios of wave breaking. This is classified based on the linear instability growth rate lambda. When this lambda is relatively large, internal gravity waves directly breaks through the gravitational instability. Therefore, the resulting state is strongly nonlinear turbulent. On the other hand, when this instability growth rate is relatively small, weakly nonlinear interactions dominate the system. Then internal waves breaks at much smaller spatial scales. And in these simulations, parametric subharmonic instability excites low-frequency internal waves. And the final state is the Garrett-Munk-like frequency spectrum. So depending on the wave breaking scenarios, we identified two types of scaling relationships that exist for the energy dissipation rate. Second, I'm showing another case of the small-scale instability of plane internal gravity wave. So this is a situation Manny talked about today. So we consider plane internal waves propagating in a stratified fluid and consider a parametric instability or parametric subharmonic instability in this wave field. So this is the calculation conditions. Conditions and schemes are almost the same as the previous elliptic vortex case. Here I'm showing the result for the case when the base wave has fluid number of 0.4. Now I'm showing the surface of the calculation domain colored with the buoyancy perturbation. So in this way, in the present simulation, the domain shape is distorted periodically in this direction. And we'll see a striped pattern over disturbance waves, so that will soon break to produce much smaller scale turbulent fluctuations. I'll show you the movie again. Okay. This striped pattern is made from the parametric subharmonic instability, and it will break to produce almost isotropic turbulence. And in this simulation, we quantify the mixing coefficient. In a model, now the kinetic energy and available potential energy are lost via the viscosity and diffusivity. Okay. And the ratio of these two dissipation terms is a mixing coefficient. As I mentioned in the introduction, this mixing coefficient is often assumed to be 0.2. But in our simulation, every case, this mixing coefficient gamma is greater than half. Therefore, the mixing efficiency is much higher than the typical values. And this gamma increased with the fluid number of the base wave and reaches as high as 0.8. The high mixing efficiency in a simulation may be ascribed to the direct supply of the available potential energy to the turbulence. In many numerical simulations, people consider the Kelvin-Helmholtz instability. In that case, the base state does not have the available potential energy, and the turbulence is generated by the kinetic energy supply. In the present case, because the base internal wave has available potential energy, it directly drives the turbulent motion. That is why the dissipation of available potential energy may become larger. Finally, I also briefly talk about our ongoing work. Now we are carrying out numerical simulations including the Coriolis effect. This study is collaborated with Mani and his PhD student, Abiram. Our motivation is to make the model more relevant to the actual oceanographic situations and explore the turbulent mixing resulting from the internal tide. When we include the rotation, partitioning of the internal wave energy between kinetic energy and available potential energy is modified depending on the wave frequency. And this expression involves the Coriolis parameter F. Therefore, we expect that there may be a latitudinal dependence of the mixing efficiency for the tide-induced particle mixing. In conclusion, we are carrying out numerical simulations of internal wave breaking using a distorted domain model. We already have 2 published papers, and this project is still going on. That's all. Thank you for listening.
Thank you very much. Now it's time for questions. Carsten.
In the lower right example with the eddy, how large is the eddy? Is the eddy like the circle there, or is it much larger as your model domain?
Conceptually, we are considering a very large scale eddy, but now this eddy is idealized a constant velocity shear, so it does not have a scale. The intensity of the eddy is parameterized by the Rossby number and the electricity, so I cannot answer how much the eddy is. The important thing is that this eddy has Rossby number of order 1. I guess it is typical around 10 kilometers in the real ocean.
Yeah, and your model domain is much smaller.
Yes, much smaller. Okay, model domains are around several thousand of meters. Sorry, I do not remember well, so we can check it in our paper.
Okay, but that's then not an order of magnitude different, right? So I was wondering if you can also do the same thing in a normal model without, where you just put the eddy in and then resolve everything.
I think it's also possible, but because our purpose is to do numerical simulation with high resolution as high as possible, I think that is why we adopt this method.
Yeah. Thank you.
Thank you so much.
More questions? I have one. I don't know if I missed it. For the simulations, do you have constant stratification?
Yes, stratification is constant because for this model, the spatial gradient of the buoyancy in the base state should be constant in space. Therefore, this number B involves a stratification n, and it should be constant. Or it can possibly be a function of time.
Thank you. Yeah. Thank you. Okay. I think that's it. So thank you very much for the nice presentation.
Thank you so much.